Since it's like after the long bank holiday weekend, so I saw that in the morning it's really kind of a good time to talk for organizer a seminar. So, but I will really try to stay quite gentle and not to introduce too complicated notions. Okay, so this is the outline. I would like to talk about buildings, surfaces, arithmetic side of buildings, geometric side of buildings, squares, products of trees, and fake projective planes and quadrics. Okay, so first of all, like buildings, as we all know, are very exciting geometric objects introduced by Jacques Tits, and they have algebraic, analytic, number theoretical aspects. So buildings consist of chambers and apartments satisfying certain set of axioms. And let's start really with one-dimensional building. Maybe it's a spherical building, maybe it's the most famous building. So it's a so-called Hebut graph. And of course I had to ask, maybe this is as an exercise, but I will tell it straight away that chambers here are edges and apartments are cycles of length 6. So you may also check the most important property of buildings, that whenever you pick any two chambers, they are contained in an apartment, right? So you can pick any two edges of the graph and they will be contained in a cycle of length 6. Okay, but now one-dimensional Euclidean buildings. What is maybe the most famous example of a one-dimensional Euclidean building? It's a Kelly graph of a free group on two generators. So, right? Everybody remember this graph, wedge of two circles? And we look at the universal cover of the wedge of two circles. And of course it looks completely trivial, but why we talk about universal covers? I'm going to give examples of much more complicated objects such that their universal covers are buildings. See, like in one-dimensional case it does work quite easily, but we will mainly work with buildings of dimension 2 today, and they will arise as universal covers of certain finite complexes. Okay, now I think it's time to define two-dimensional buildings, and we will define in the same time Euclidean and hyperbolic buildings. So we say that two-dimensional Euclidean or hyperbolic building, it's a two-dimensional complex such that it's a union of tessellated planes called apartments. And for any two chambers, there is an apartment containing both of them. So chambers are polygons in our tessellations. And if two apartments have a non-trivial intersection, then there is an isomorphism of the apartments fixing their intersection pointwise. Right? Okay, it's just a bit of entertainment. It's kind of an example of an apartment. Of course, it's like cheating, but yeah, still, there is a tessellation of a hyperbolic plane behind. Okay, now a couple of essential definitions, which also everybody knows, but maybe just every time one should define what is meant. By polyhedron, I mean a two-dimensional complex, which is obtained from several decorated polygons with words on the boundary. And how we get our polyhedra, we identify sides with the same lattice respecting orientation. And you see here, we already have an example of an Euclidean building with the link, which is a Hebut graph, right? So if we take those 7 Euclidean triangles and we identify like x naught with x naught with x naught, x1 with x1 with x1, and so on. We get a complex with just one vertex, and the link at this vertex will be the Heawood graph which we had on the first page. And the universal cover of this complex is a Euclidean building, right? We already kind of revised the universal cover when we look at the Kelly graph of a free group. So we already have all the definitions revised. Okay, now just a reminder of a link. So saying, you have your polyhedron and take a vertex with a center in one of the vertices of this polyhedron, and then we look at the intersection of the polyhedron, the sphere. It will be a graph, and we will call it a link in this vertex. So for example, here, of course, it's quite easy example. If you just take a tetrahedron and look at this vertex, then the link is just a triangle. Okay, sometimes it's useful to introduce the lengths as a just angular lengths at vertices, but sometimes we are just happy with the combinatorial definition of a link. And also this kind of geometry is induced by just by combinatorics of the building. Okay. Now also we will consider thick polyhedra. We are interested in buildings and in complexes where every chamber is contained in at least three, where every edge is contained in at least three chambers. So any questions so far? We just went through the definitions and examples which everybody knows, but it's kind of always a good idea to have an easy start. Okay, so again the Heawood graph, but also with the labeling of the vertices which are induced by those 7 triangles, right? You may ignore the labelings, but you may also follow it. It just this labeling is induced by the labeling of the triangles, and 2 more notions for the graphs. We define a diameter as the maximal distance between 2 vertices, and a girth at the length of the shortest cycle. So here we have that between any 2 vertices, the maximal distance between any 2 vertices is 3, and the girth is 6. Right? So this is a generalized quadrangle.
Alina,
Yeah.
I didn't see any labels like X51 on the.
Yeah. Sorry, it's just a mistake, right? It was considered to be inverses of the. You see, very good. This one, it's actually inverse. It's
Oh, it's
X
like,
not.
it depends on the orientation of the edge. If
It
it's
depends
pointing
on
out
the
of the vertex
orientation.
or into-
Yeah, so you see, it's good that
Okay.
to see that people are paying attention. Indeed, this once it's like reversed orientation of the edges. Yeah, because like if you have a triangle, right, your vertices of your link will be here and here. So each edge contributes 2 vertices, saying one black and one white. So this was to distinguish black and white vertices. Okay, good, well spotted. And why it's nice to construct such polyhedra with given links, of course maybe this fact was known in the community, and I'm sure that it was known to teach, and yeah, but I think it's a kind of nice reference. It's a paper of Ballman-Breen in Publications of IHS of 94, and also their terminology is maybe more complicated and they consider more general cases, but kind of for 2-dimensional buildings it's really quite nice formulation. If we just say that, okay, say we have a 2-dimensional polyhedron, and if all the links are graphs of diameter m and girth to m, then the universal cover of this polyhedron in this two-dimensional building. Okay? And so also about 2000, I introduced a kind of combinatorial way how to get polyhedra. So saying the idea is, okay, I decided really not to give the definition because the definition is really quite long and technical. But the idea is the idea is quite simple. It's to have a set of words and with some additional combinatorial properties such that we are getting given links at vertices, right? And I will give a lot of examples of such polygonal presentations, so it will be clear what I mean. But this I already gave the first example with the 7 triangles, right? That we get a set of polygons with words on the boundary, and then we glue them. When we glue them together, we get a polyhedron with given links.
Are the chambers always triangles?
No. This is the thing that chambers can be anything.
The Ballman and Brin thing?
No, in Ballman and Brin it was, that's why I said that it's slightly modified version of Ballman and Brin, because in Ballman and Brin it was either triangles or squares, and actually they considered Euclidean case. But their proof works exactly the same for the hyperbolic case as well, that if we just say that, for example, which an example which I will have later, we have triangles, but hyperbolic triangles, and the links are generalized quadrangles. But also in this construction, which I had about 2002, it can be any polyhedron with, here it was for polygons with even number of sides, but any number. So it just, so this this construction just I was talking about it a couple of months ago on Henry Wilton's seminar, but I would be happy to discuss it later. Just today I would like to move on, but but in general it can be any number of sides. Okay, now let's talk about kind of geometric side of buildings, and we will talk in this section. We will talk about hyperbolic buildings. I think everybody knows this old, long-standing question of Gromov: is it true that every one-ended hyperbolic group contains a surface subgroup? And most known examples do support a positive answer to this question, that how it goes so far, that everybody picks their favorite groups, hyperbolic groups, and then at some point proves that there is a surface subgroup. So, and of course the history of this subject, I will apologize to anybody whom I didn't cite, whatever, because there are of course a lot of papers in this subject, but with relation to hyperbolic buildings, I kind of showed it that with even-sided chambers, then for any groups acting on Bourdon buildings, it was Footer and Thomas 2011 for random groups Caligari and Wolke, then Kalin Markovic for fundamental groups of hyperbolic three manifolds. Henry Wilton showed graph of free groups with cyclic edge groups, but still there are examples of groups acting on cut zero spaces which don't have surface subgroups, right? And so there is a paper of 2008 of Chris Sergeyev and Sapir for certain classes of right angle Artin groups which may not contain surface subgroups. So this is still, it's like similar flavor, right? So what is their proof? Actually, their proof is computer based. They just pick certain right angle Artin groups and show that you cannot embed surface there in any possible way. And I would like to talk about still a source for possible counterexamples, at least like with Riikka Kangaslampi, my collaborator from Helsinki. We have some groups acting on hyperbolic buildings, such that for some of them it's still not clear if they do contain surface groups or not. So first of all, several words about these groups, that how it fits to the framework which I already described. So we have we get a set of hyperbolic triangles with angles pi over 4. And we get buildings with apartments which are tessellated by these equilateral triangles. And the links of our buildings are generalized quadrangles. So you see this graph looks slightly similar to the Fano plane, but it's bigger. So there are 30 vertices and 45 edges. And okay, again an exercise, what is the diameter? Do you see what is the diameter of the graph? Yeah, 4. And what is the girth?
8.
And the girth 8. Yeah, very good. Great to see that people are paying attention to what you are saying.
Maybe I want to cheat at the exercises.
Yeah, so now if we say that we are interested in groups acting simply transitively on this kind of buildings, then, and saying, let's say, torsion free, then just we have found there are 23 non-isomorphic groups, and it's found by computer search, not only because it would take forever, but it's kind of clever computer search. Okay, so let's.
Is it clear that the 23 aren't non-commensurable too, or do you know?
This is a very good question. So I know that there are 2 sets which are not commensurable. But if they are commensurable between themselves, I don't know. This is a very interesting question, because actually all the examples which I bring up today, it's kind of a more invitation for a discussion that I would be happy to discuss this later, because one, it's like for specialists. There are 2 buildings where these groups act, and just by general reasons, one of them is a Kac-Moody building. But it's not clear if the groups which act on this Kac-Moody building can be embedded to the relevant Kac-Moody group, because the automorphism of the building is really huge. But it's kind of interesting question which would be good to discuss. Okay, so now examples how these groups look like. So like 2 of them. So what is the notation? I promised to show examples of polygonal presentations, right? This is what I mean. We have sets of lattice, right? And of course the order matters. And then this is how the triangles look like. We pick a triangle and we write a word in the boundary, and then it's really similar to my first example. We just glue everything together to get a complex. This graph is the link, and then we at the universal cover we get a hyperbolic building where these groups act simply transitively. But as I already mentioned, it turned out that there are 2 non-isomorphic buildings. So we have, right, because the groups, how we get the groups, we get them in kind of combinatorial way, just to get this link. And then it turns out that they give rise to two buildings because there are two links of order 2. It's also kind of computer search because even the first link is quite large, but the second link is even bigger. But there are two buildings. Okay. And now, yeah.
Are these things like special combinatorial designs? People sometimes talk about these things where you have like a subset of things and then you pick other.
Indeed,
subsets
they are not designs. Yeah, I'm an expert. I was teaching in Newcastle for like 5 years a course which is called Geometries and Designs.
And they're not.
Yeah, but now I'm on sabbatical, so the course is gone because it's like very, very nice course to teach designs. So this is not, it's quite interesting that the example of a two tilde group, which I showed on like one of the first slides, is a design at the same time. There are more extra symmetries, but these hyperbolic examples, they don't have any symmetries. So the building, of course, the building has a lot of symmetries, but if you just take a polyhedron itself, it doesn't have any symmetries, no design properties, nothing. It's really kind of strange, and they exist for no reason. So that what is also quite interesting, that when we talk about groups acting on products of trees on buildings, very often one can find some infinite series of examples which come from some arithmetic, and I will talk about such examples a little bit later. But these hyperbolic examples, they exist for no reasons. I already mentioned that we have found them by computer search. But what is kind of interesting about these groups, we still don't know if they are residually finite or not. And also some of them, we don't know if they contain surface groups or not. Of course, like general belief that they should, right? We would discuss this with various people, but still it's not, at least they don't have obvious surface groups. And amongst those 23 groups, so we have some kind of evidence of in the negative direction. It's of course not too strong. We can just talk about genus 2, but still like 19 out of 23 of our groups don't have periodic apartments corresponding to a surface group of genus 2. So what is happening in the hyperbolic buildings, that if you manage to find an apartment which is tessellated by some kind of fundamental domain, which can look quite bad, but still, if you find a fundamental domain to tessellate your apartment, then you do know that you have a surface subgroup. Yeah, but so we at least can say that most of our groups don't contain these actions of a surface.
What about property T?
They don't have property T. It's quite interesting that if you take the criteria of Ballman, Svetkovsky, and Zhuk, that we know that if you manage to get such groups, but for much bigger links, so this is where like the computer power stops so far, because you have to deal with a graph with like about 700 vertices. Yeah, so it's one has to have some kind of clever idea. So we know that there is it would be property T in such groups, but this link is too small for a hyperbolic group to have a property T, and just they don't have, because some of them do have infinite abyllinizations. Again, like most of them have finite abylinization, but I think there is one or two groups which have infinite abyllinizations, and it just kills the property T. Yeah, but now to show that any case we can find surface subgroups in 4 of our groups, but just to show that it's not obvious. So what is the difficulty? that we have those 15 combinatorial types of triangles, and then by the Gauss-Bonnet formula, we have to have 16 triangles to get something which looks like a fundamental domain. And also, what is the difficulty? That we have to be sure that when we glue our surface out of those triangles, that the sum of the angles is exactly 2 pi, right? So I just mentioned that there were already some attempts of people to prove that any group which acts co-compactly on the hyperbolic buildings does contain a surface group, but actually there was a mistake there, and the mistake comes from this fact that it's very difficult to ensure this kind of combinatorics, that you can have like crazy group, but then how do you ensure that this sum of the angles is 2 pi? Of course, you can just, by general topological reasons, you can say, okay, there is some kind of topological surface which you can glue from your like polygons or whatever, but how to ensure that it really can get tessellated in an apartment, then it's kind of difficult. So yes, or what is the ideas of the proof? The ideas of the proof are really quite straightforward. Just we look at the tessellations of surfaces, graphs embedded into surfaces, and like various kind of nice combinatorics. Because of course we have this kind of tessellation by triangles, but we look at the dual graph, which is a tessellation by octagons, which is feasible, at least for genus 2. Okay, and this reminds, I have found this painting by Joe Lees, the whole world compressed in a circle. It's exactly about this tessellation of octagons and triangles. Okay, so any questions about the geometric part?
So what is special about genus 2?
The genus 2 is special because the graphs are quite small, so we can still fit them into the computer, right?
Still LP problem, isn't it?
Sorry?
Isn't it LP problem? So like genus 3 or higher complexity is too high, is that what you're saying?
Yeah, it's really just difficult. We started actually just genus 3, we didn't go through all the cases. For genus 3 we considered fair amount of cases. We didn't find any subgroups, but it's just very large number. Yeah, even 2. Yeah.
But so all you have to do is fit these in genus 2. You just have to fit some 16 or something of these triangles together, so that all the identifications on the boundary make a surface.
Yeah.
You don't have to actually check in advance how it sits inside the building. You just need to close up.
You don't need to check how it sits in the building, but you have to check that this. If you glue a surface, you have to check that the sum of the angles is 2 pi. Yeah, and by Gauss-Bonnet it should be like 32, and then every time you get 16 triangles, it's like the formula. It's of the number of triangles, it's 16 minus 1. Yeah. No, I would be happy to discuss how to deal with this question, because it's quite interesting. Because there are computer methods of like Danny Caligari and like Henry Wilton was also doing some computer search, but with Henry we already tried, like it doesn't seem to work. It's not an exact science, right? It's not a proof, but just these methods don't seem to work for these groups. Okay, so now let's look at the arithmetic side of buildings, and we will talk mainly of products of trees later, but now we just talk about trees. Okay, now let's do elementary number theory. So it's kind of very old result of Jacobi. If you have a just odd prime and the number of such 4 tuples of 4 numbers such that their squares, the sum of the squares equals to p, it's 8p plus 1. And let's look at this case, which is the easiest one when p is 1 modulo 4. Then there is exactly one aj is odd, and the number of representations with a not odd such that, okay, a not is non-zero is p plus 1. And of course the result is very old and classical, but there is a consequence for like integer quaternions. So now let's look at quaternions, and these are the quaternionic relations. And let's look at this set SP, and this is exactly p plus 1. It's a kind of elementary exercise in number theory. Okay. And so it's also another observation that you can define a map psi p for every odd prime to PGL 2QP. Right? You can really use the quaternions to define such a map. So this is kind of also elementary arithmetic. We know that if we have a square, right, which is minus 1 modulo p, has a solution in z, then by this lifting Hansen's lemma in kind of elementary arithmetic, we know that there is a solution in QP as well. Right? But indeed, this was kind of ingenious application of this kind of very classical facts of Lubotsky, Philip Sarnak when they constructed Ramanujan graphs. Again, I will not talk about Ramanujan graphs, but just what I'm interested in, it's that this set of the images of the map which I just described contains p plus 1 elements, and they generate a free group of rank p plus 1 divided by 2. And do remember, I started with a Kelly graph of a free group, and indeed this group gamma p acts freely and transitively on the vertices of p plus 1 regular tree. I think we will denote it t p plus 1. Right. So okay, but now what happens for the products of trees? And we had a very nice course of Pierre Emmanuel about groups acting on products of trees, but I thought that it's kind of a good idea maybe to add this kind of arithmetic side of groups acting on products of trees. So in fact, infinite series of lattices acting on products of trees of different veloces, I mean arithmetic groups in this case, like Bulgar-Moses examples, and they were slightly generalized by Ratagi, who was a student of Mark. And so what was his generalization that I think Mark and Shar, maybe even it was also paper of Shar Moses of something like even 92, quite old, when he looked at 2 primes which are 1 modulo 4, and actually it was an ingenious observation that if you just take 2 different primes and you take 2 of those maps for different primes, and then you take saying another prime is L. So you take gamma P and gamma L, and those gamma P and gamma L indeed generate a group which acts on the product of two trees. And moreover, the group is arithmetic in the direct product of PGL2QP and PGL2QL for this different prime. And it's actually work in progress, but I'm almost sure that it works, that one can take actually any number of trees, but there is a little bit of more of arithmetic geometry in the way that this equation should be more complicated. So for this one, you really need this P1 modulo 4, but for, like, you can really generalize this construction for any number of trees, and but just it has to be more complicated equation here. Okay. Yeah, and then Rattaghi, he did for any two different primes. They don't have to be 1 modulo 4. And then it took really some time, that even so it's quite a popular object, but still, for what happens for the product of two trees of the same valency. So with Jakob's sticks, we had also like infinite series of arithmetic groups acting on products of trees of the same valency. And the question is, why it's suddenly like, what is the difficulty for products of trees of the same valency? And so the thing that one should move out from Hamiltonian quaternions. Of course, this construction which I described now, which was used by Lubotsky, Philip Sarnak, and then by Burger Moses Rattaghi, it's really very neat. It's just one, right? It's just one group for any set of primes, and then it really works very, very nicely. But it turns out that for products of trees of the same valency, one has to move away from Hamiltonian quaternions, and one has to look at more general quaternion algebras. But what I realized, if you just talk about quaternion algebras, then people get bored and asleep, and especially if you draw a Hilbert symbol, it's really like killing. So what I decided to do, I decided to just modify the quaternionic relations, the quaternionic multiplication, and then it looks almost like before, but slightly spoiled. So what is, it's again like an exercise for the second half of the talk to find it, to see why it's different from the classical quaternionic multiplication. You see here we have this variable t, because instead of Hamiltonian quaternions, instead of integers, we have pqt. So here we have, and now, of course, this kind of building, which is a product of two trees, I already mentioned, right, that we are interested in groups which act on products of two trees, we can guess explicit group presentations. And in fact, this is, I'm really very happy that Pierre Emmanuel is here, because this is his group Gamma 1, with which he started his lecture course. So this, and how one can see that it's really an arithmetic group. So you see there are 4 relations, and just to remind how it again fits to the framework of my talk, how we can look at this group. We take 4 squares and we write words on the boundary of the squares, and then we get them together by gluing the sides with the same lattice respecting orientation, and then the universal cover it's a product of two trees. Because, and another exercise, what is the link in this case? So the link in this case is a complete bipartite graph 4-4. So everybody has to be connected with everybody. Okay, and now how we get the relations. Indeed, this was for this particular group, it was a magma search to find the explicit quaternions. And indeed, if you replace here like a 1 by this quaternion and so on, you indeed get, it's like by some miracle, everything cancels out and you get relations, right? It's really kind of to put hands on the concrete examples. And this is for p equal to 3. So, okay, but now more about this group. We can really put it into the framework of buildings, like I was talking before. And this particular group is an arithmetic lattice in the product of PGL2 F3 double brackets T with itself, right? So it's kind of two trees of the valency 4. Okay, and this is kind of gentle formulation of our result with Jakob stick that we can get really a family of groups acting, of arithmetic groups acting on the products of trees of the same valency, but also that the number of non-commensurable classes of such groups for each q, it's q plus 1 divided by 2. So here, because it's like we have some arithmetic behind, we can also have we can say that our groups for the same valency are non-commensurable, right? So this is also kind of difference from the previous case of Hamiltonian quaternions, which I just now described, that for Hamiltonian quaternions, for any set of primes, you get one group. But here, you have this prime power, and then you get a series of groups, like you get at least the q plus 1 divided by 2 non-commensurable lattices. Okay, so I'll just skip, and for specialists, I will, because I saw a question in the eyes of Pierre Emmanuel and David, that what about the general construction, right? You can ignore this. You may either ignore this slide, or you can look at it. Just it's a kind of honest result. What is happening? So you can see why I was trying to give like really a nice example, kind of not to scare everybody straight away. So what we do, we really have those two parameters q and tau. So our trees will be of degree q plus 1, but then we have also this tau, which comes from arithmetic of our fields. Okay, and then these are the groups which they do act on products of two trees, but they do have torsion. But then how you get into torsion-free subgroups, the torsion-free subgroups sit there with index 2 multiplied by q plus 1. So like you can, here you have this. So what is kind of a trick behind that? All those group presentations which act simply transitively, they also have a dihedral group which acts on it, and we are really using it. It turns out that those overgroups are easier to kind of to handle, and then to get to the index 2 multiplied by q plus 1. Okay, but this is just to say that there are all those parameters, they come from certain number theoretical inequalities. And I would like to finish with some subject, like you say that how like ideal talk, right? That and there are several versions that last 5 minutes only the speaker understands, but another version that lasts 5 minutes nobody understands. So yeah. so I think this is really the 5 minutes. No, the previous 5 minutes were like the speaker vaguely understands, right? But now it's really nobody understands. But nobody, no, not in the audience, just nobody at all understands all the subject. I also discussed this with several people. Like we just in the morning we discussed with Thomas Vilzant that it's really kind of a fascinating subject, but more or less nobody understands all the details. And there are reasons, because various proofs and they really go from like very hardcore analysis of harmonic maps, which actually I deleted from my talk because I saw that it was enough any case, and to the arithmetic geometry. And yeah, so for example, Gromov does understand, but like very general picture, and to fill in details, it turns out it's really quite difficult. So, but what is the subject? It's like fake algebraic varieties. So what are the fake algebraic varieties? What is the idea of fake algebraic varieties? It's to have, saying, complex projective plane, right? But to have some variety which has exactly the same invariance, like Betti numbers, Euler characteristic, which is the complex projective plane, but which is not, right? And this was like the first example what was constructed by Mumford in '79, and it's still this construction. I think there are very, very few people who understand all the details about this construction. Again, most likely that no one. Yeah, but then nevertheless, those fake projective planes, they were classified, and there was like Prasad Young paper in Invenciones, which kind of gave a framework of classification, but they thought that they already classified all of them, but it turned out that not. They claimed that there were 18 of them, but it turned out that there are 50, right? And you see, like it's like who did it? It's Cartwright and Steger, but again, they have like very complicated programs which no one rechecked, right? So yeah, it's not clear how many exactly, but at least there is an algorithm how to find all of them. Yeah. So, and I think you already noticed that like Cartwright Steger's people who were also looking at groups acting on buildings. It's really very, very similar type of mathematics which I was describing today. You have to find some methods to find the relations, and yeah, so kind of some geometry behind. Yeah, and then okay, but at least with fake projective planes, why the classification was possible? Because it was known that all those fake projective planes are complex Ball quotients. But now, if you talk about what are the fake quadrics, it's something which has the same invariance as SP1 cross SP1, but then there is no such a analog. We cannot say that they're Ball quotients or whatever. So that's why it's not even clear if the full classification is possible. But nevertheless, there are like examples of Bovil, Hirzebruch, and other people. But what is again? What is the relation to my talk today? It turns out that the key ingredient, at least of existence, of such fake projective planes and quadrics, is really arithmetic lattices acting either on buildings, on products of trees, or on some kind of interesting objects. And so the motivation of my collaborator Jakob Stix was to get some kind of fake quadric and in a way, maybe mimic the philosophy of Mumford's philosophy for fake projective planes to get it for products of trees. But then, indeed, this arithmetic group, which I showed for p equal to 3, right? Yeah, so this group indeed gives a fake quadric, but a fake quadric in finite characteristic. So it's not a complex surface. It's still like algebraic surface, but in finite characteristic. And also it's not clear why nobody, and maybe they don't exist, right? So what is so far kind of open, and I would be very much interested to see why, if you have like PGL to QP cross PGL to QP, why, for example, one cannot find a group checked simply transitively on product of two trees, at least for small primes. So with computer search, I did show that like for p equal to 3 and p equal to 5, you cannot find anything which is like PGL to QP, but two copies of PGL to QP, but not clear what is the kind of mathematics behind it. Okay, so thank you very much for your attention.
You fake quadrics.
Yeah.
The fundamental group are lattices somewhere.
It's a really good question. We really can say only about this, actually I don't know. I can only talk those methods. Yeah, so what is kind of interesting question which we discussed before with Thomas, that you have, so what happens if you have a arithmetic lattice acting on either like products of trees of a building, then there is some kind of magic procedure coming from arithmetic geometry that puff, there is a fake quadric or there is a fake projective plane, but then this object does have a topological fundamental group as well. And the question, what is this discrete group which is topological fundamental group? And the answer, we don't know. And what is the relation with the group which you started with? It's also not known on the level of discrete groups. But from arithmetic geometry, it follows that if you look at the profinite completions of both groups, then this kind of group which acts on a building is a homomorphic image of the profinite completion of the topological fundamental group of your variety. Yeah, and this is kind of mystery which I really would be really happy to discuss and to hear what people think about it.
Simpler question going back to earlier in your talk. Do you know any examples of hyperbolic buildings that contain surface groups where the surface group isn't in the stabilizer of an apartment?
No. Yeah, the answer is simple, and I kind of hope that, okay, maybe not for all hyperbolic buildings, but at least for those triangular buildings, I do hope that maybe if you have a surface group, maybe it should be a stabilizer of an apartment. And with my collaborators, Georgios Koulopoulos and Chika Messe, we had an attempt to prove this using harmonic maps. As I said, that I just didn't talk about it now. And we had an attempt to show this fact. But then it turned out that we have to add additional conditions, and the kind of best corollary of our result, it's an old result of Bonk and Kleiner when they add an additional condition that the Hausdorff dimension of the limit set should be 1, then you do have a you do have a plane with the group action, but potentially our statement is stronger than Bonk and Kleiner's statement for buildings, but we don't know if there are any examples in between them. So it's a very interesting question.
So Can you map a hyperbolic plane into product of trees, quasi-isometric?
This I don't know.
Yes, you can. It's
You
on.
must be able to.
No, I
It's-
think there are results, right?
If you want finite valence trees, if you want, the kinds of trees she's talking about, rather, infinite valence trees is easy.
No, finite.
Finite valence trees, it's a hard theorem of Buelow, Drenishnikov, and Schroeder.
Yeah, so I thought that the Drenishnikov and Schroeder.
Yeah, I mean, I wish I understood what was really going on in that theorem. It's true, and they have a proof, but it's a very long, complicated construction. They take the map into product of two infinite valence trees, and they have a method of pruning it to get it to land inside a product of two trivalent trees inside of there.
Yeah, that should be more transparent.
Yeah, no, this is very interesting. No, I didn't know that it was not known. It just David asked me 2 days ago, but like for the week during the weekend I didn't have time to solve it. Yeah, what I hope maybe what to try is to play with these methods which I mentioned of Sergeyev, Sapir, and Crisp, when they show that in some kind of right-angle arcing groups we don't have surface subgroups, so maybe for some of the groups acting on buildings, some similar methods would work. But as I said, I'm really happy to discuss. No, it's really great to have so many experts right at it. Of course, I apologize for the slow start, but it's like after the bank holiday weekend, we had to wake up.